Hello and welcome to lesson number 9. This is the fourth lesson in Unit 2B in our grade 10 academic math class. This is sine and cosine law applications. So essentially this is just kind of like word problems where we're not specifically telling you you're going to use sine law, you're going to use cosine law. We're leaving it more up to you interpreting the situation. So at the beginning, let's just recall that when we have non-right angle triangles, if we're going to use the sine law, we need to have a corresponding side angle pair, which is like an angle in the side across from it, and then another piece of information from somewhere in the triangle. Otherwise, we're going to use the cosine law, which we do in cases where we have 3 sides, or in cases where we have 2 sides and the contained angle between them. Let's just jump right in with example number 1. A greenhouse is 10 meters wide and the rafters make angles of 25 degrees and 60 degrees with the joists. Find the length of each type of rafter accurate to 1 decimal place. So I've done a little setup over here and you can see it. I've drawn the situation with the width of the greenhouse and then the rafters and the appropriate angles and the measure 10 meters. What I've added in is that, and this is similar to the way that we worked it when we were doing the sine law lesson, is that we are able to quickly and easily find the third angle in the triangle. And what that creates out of the gate for us, which is nice, is a side angle pair. So once you've got a side angle pair, we're off to the races. We can use sine law. What we're looking to find in this question is the length of each type of rafter. Now you'll notice that I've called them A and B. I just picked those letters. It doesn't really matter what you call them. I picked A and B. You'll notice that because this is a word problem, we are going to define our variables. So I have done so by saying let A and B represent the lengths of the rafters in meters, and that's an important part to recall that we are going to be always including units of measure when we are defining our variables. So let's go find little a to begin. So we're going to set ourselves up a sine law here. So because I haven't assigned any other letters other than a, little a rather, we're just going to set these up directly. We're not going to use any intermediate steps with letters. So let's go with the sine of 60 degrees over little a is equal to the sine of, I think it was 95 degrees over 10, yes. So we've got our side angle pairs in there. We see our a is in the denominator. We are going to cross multiply. So let's get that happening. We've got 10 times sine 60 degrees is equal to a times sine of 95 degrees. We are going to isolate a by dividing both sides by sine of 95 degrees. And now we are going to type this whole mess into our calculator and see what we get. So we've got, it's 1 decimal place, so 10 times sine 60 equals divided by sine 95 equals, and that is 8.69, so we're going to go with 8.7 meters. Is approximately equal to A. All right, 1 rafter down. Let's go get the other one. So we're going to find side little b now, which is the other rafter. Let's set that up as well. So that is the sine of 25 degrees over little b is equal to the sine of 95 degrees over 10. Same thing, we got our side angle pairs happening there. Let's try to make that look a little bit more like a 5. And we are going to, as before, cross multiply. Let's get that happening. So we've got 10 times sine 25 degrees equals b times the sine of 95 degrees. We isolate little b by dividing both sides by sine 95 degrees. And now we're going to type that whole mess into the calculator and see what we get rounding to 1 decimal place. So let's clear it out. Here we go. We got 10 times the sine of 25 degrees equals divided by the sine 95 degrees equals, and that's going to be 4.24, so just 4.2 meters is approximately equal to little b. Because this is a word problem, we need to sum it up with a therefore statement. So therefore, the rafters, I did not start that in the right spot. It's a little bit close. The rafters are 8.7 meters and 4.2 meters. And put ourselves a little box around it. Pretty close to my calculation. And we'll call that a day. So there we go. The drawing I find is a very helpful step, the diagram, so that you can figure out exactly what you have and don't have. And hopefully that will give you an idea. Is it a non-right angle triangle? Yes. And then do I have a side angle pair? Let's jump in here to example number 2. From point A, the angle of elevation to the top of a transmission tower is 61 degrees. At a point B, 52 meters closer to the base of the tower, the angle of elevation to the top is 71 degrees. How high is the tower accurate to 1 decimal place? So this is neat. We actually have some right angle triangles hanging around in this one. Let's get this information onto the diagram here first. So I just sketched this out. We've got the top of the T for tower. Maybe we'll put C down here at the base, just to have a letter there at the bottom of that. And we've got point A, which is the first reference point B, which is closer, and then I've already labeled side little h on there for the height of the tower, but let's get those other pieces of information in. So point A, angle of elevation to the top is 61 degrees. All right, we got 61 degrees happening here. We know that at a point 52 meters closer, the angle of elevation, I believe, is 71 degrees. Yep. So we've got 71 degrees happening there. All right, so we've got here a piece of information that we want, which is this guy, but we can't get to it right now because the two right angle triangles, and you don't have to do this on yours, but you can just watch me do it. We actually have two right angle triangles. We have TCB, but we only have one piece of two angles, but no sides, so that doesn't help. And we have TCA, but again, we only have one partial side length, two angles, and that's it. So what we need to be able to do here is work with, let me just clear that out because that got dirty really quick. Here we go, we're going to be looking at something from TBA first because we have an angle and we have a side length. We need to get some more information about this first, so let's work through some of that. So what's neat about straight lines is that this is a supplementary angle, which means that 180 minus 71 is going to give us that angle right there. So we have an angle there of 109 degrees. Right there on the inside. That's angle B, I guess, that little triangle. And we can subtract those two angles from the sum of the interior angles, which is 180. So that's 261, 70. That's 10 degrees up here. And this little wedge, that's going to be 10 degrees. So that's looking good for us. I guess while we're here, we might as well find that last one as well. If we have 180 minus 90 minus 71, that's going to tell us that we have 19 degrees here, just in this little wedge, just because I'll make that look like a 9 too. 9. There we go. Okay, so that's looking pretty good. Now we have some information here in triangle TBA. We have a side angle pair, which is great. This is just going to be it's going to be crowded in there, but let's do it anyway. We have 10 degrees here, and then we have the value of the side across from it. So if we have a side angle pair, we're going to use the sine law. Now, which piece of information here will help us most? Do we want side TB, which is this guy here? We could. Do we want side TA? Also valuable. Depending on which of these two right angle triangles you want to use at the end of the day, it doesn't really matter. I guess because I did it first, let's find TB. So let's make that our instruction. So let's get let H represent the height of the tower. The height of tower, and that is measured in meters, I believe. In meters, that's looking good. And number one here, we are going to find side, what did I say, TB, I think. Although honestly, you could find TA, be the same thing, doesn't really matter. So in finding TB, we're going to articulate our first side angle pair. We have the sine of 10 degrees over 52 will be equal to, so let's have a look. We're going to use the 61 then, because that will be the one that is across from side TB. So we have the sine of 61 degrees over side TB. And now we cross multiply. There we go. So we have TB times sine of 10 degrees equals 52 times the sine of 61 degrees. We isolate TB by dividing both sides by sine of 10 degrees. And then we have TB being equal to approximately, so let's see what we got here. We got 52 times sine 61 equals divided by sine of 10 equals, and that's going to be 261.9. 261.9 meters, and it's 269.910. So, we'll just go to 1 decimal place. It'll be pretty accurate there. All right, so now we have another piece of information to add to the party here. We have oh gosh, what was it? 261.9. There we go. So we got 261.9 here. And now we have a right angle triangle that we can focus on. I'm running out of good colors here. Let's go with hot pink. So we've got triangle TCB here working for us. And I guess if we want to do a little bit of a throwback to the primary trig ratios, if we have here a reference angle of 71 degrees, the side that we want is going to be the opposite. The side that we have is going to be the hypotenuse, which is right there across from our 90. So we are going to use the, well, you know what, let's not do the primary trig ratios. Let's actually do Sine Law again, since that's kind of the spirit of what we're after here. So we are going to find H now. That's going to be our number 2. Number 2, find H. And let's set ourselves up some sine law. So we have sine of 71 degrees over unknown h equals the sine of 90 degrees over 261.9. All right, there we go. Let's do some cross multiplying and make this happen here. So we've got h times sine of 90 degrees equals 261.9 times the sine of 71 degrees. We isolate by dividing both sides by sine of 90 degrees. Now something you may have noticed along the way here is that sine of 90 degrees is actually just 1, so it isn't really going to change our answer a whole lot, but let's get it anyway there. So we've got 261.9 times the sine of 71 degrees is going to equal 247. I don't remember what we were rounding to here. Accurate to 1 decimal place. So 247.63, so just 247.6 meters takes us to our answer. Let's get a quick therefore statement on there. So therefore, the tower is about 247.6 meters. There we go. Call it a day. Got the therefore statement. That's looking really good. Part of word problems is making sure that you're following the right form, such as defining your variables, maybe having a diagram that you can refer to and that your teacher or instructor can see to visualize your thinking. Little instructions like 1, find TB, 2, find H, things like that are really helpful as well. And obviously then a therefore statement summing up the word problem. We're going to stop it here. We're going to come back and do a part 2 to finish up this lesson, so we'll see you there.